All right, let's start. Now, I'm pretty sure you all know scientific notation. Don't know whether you did significant figures in year 10, but we do really need to think about what significant figures are used for. All right? By the end of the lesson, you should be able to convert between scientific notation, or it's called standard form, and decimal form. All right? You must be able to evaluate products and quotients of numbers in scientific notation using index law. You must be able to use scientific notation to solve practical problems involving significantly large and small numbers, and define a significant figure, including the laws for the significant zero. I'll talk a little bit more about the significant zero in a few minutes. All right? Now, pretty sure all of you know what scientific notation is. It is also called standard form, and it is written in the form of k times 10 to the power of n. All right? Index notation. We call your index notation. We're going to use index notation when we deal with scientific notation. Remember, k could be 1, cannot be anything less than 1. 2, k. The maximum value of k could be 9.9999999. It cannot be 10, because 10 can be written as 1 times 10 to the power of 1. All right? It is actually a convenient way to represent very large number or very small numbers, and to represent in the scientific notation, insert a decimal point after the first non-zero digit and multiply by the appropriate number of 10. Useful, think about the graphics here. If you are going into physics, where you're looking at all the atom structures and stuff like that, or even chemistry, you will have to actually represent all that in terms of scientific notation. You will not be looking at really small numbers, 0.000000001 or whatever. You will really get confused. Again, think about space travel. If you have the chance to go space travel, or if you're going to look at very large numbers, think about distance and the time. You probably need to use scientific notation. All right? Now, important thing for you to realize is scientific notation is actually a power of something. All right? You can go on and on. You can go on and on. 10 to the power of minus 3, 10 to the power of 4, 10 to the power of 3 and 4, or whatever. Think about the value and the place value. I'm pretty sure this is the one that we don't really discuss in year 10. So you need to think about how you would write it out. So for example, you should know that 1 over 100 is 10 to the power of minus 2, right? Or 1 over 10 to the power of 2. So rewriting it as a power of 10 is just minus 2. Rewriting that is 10 to the power of minus 1. So you are representing the number in terms of the power of 10. Now, so we know that this has to be greater than or equals to 1 and less than 10. So maximum we can get is 9.9999999. All right? If n is greater than 0, then the result is larger. N is less than 0, the result is smaller. All right? Which means that's in the decimal, less than 0, that is in the hundreds or the tens. All right? Now, if n equals to 0, the result remains the same, which means your number is the same. All right. So, for example, 1, 2, 3, 123, you can write in this way, this way, this way, or this way. However, that is scientific notation, the others are not. Now, if you've got 10 to the power of 3, 10 to the power of 6, 10 to the power of 9, 10 to the power of 12, those are engineering notation. You may come across that eventually. All right? So anything in terms of 3, 6, 9, or minus 3, minus 6, minus 9, think about that. 3, 10 to the power of 3 is actually kilo. Right? And 10 to the power of 6 is giga, mega. And 10 to the power of 9 is giga. So think about all that. You've got those are the engineering notation that you will learn. All right, time for you to do some exercise. the handout I gave you, you should be able to do exercise 1. 3 minutes. Some of you have done it. It's pretty straightforward, I would say. Only 4 questions. I will upload the solution a little bit later on Google Classroom. Couple more minutes, then we'll go on to the next week. All right, some of you have done it. Nice. All right, when you're ready, focus back on the whiteboard, please. Now, can we... Hey, focus back on the whiteboard, thank you. Few questions to show you how to evaluate expression without using a calculator. All right, forget about a calculator. Sometimes you don't have it with you if you've got to look at something like this. How would you do it? Say, for example, part A. How could you do that without a calculator? All right. Now, what you need to do is to group the 10 to the power 4 and 10 to the power 3 together. So I'm good doing that. 4 times 2.1, rearranging it, 10 to the power 4 times 10 to the power 3. Using your index law, you do actually know that 4 times 2.1 is 8.4, and this is 10 to the power 4 plus 3, which is 7. All right? Now, what about C? How would you do that? Or let's do B first, before we do C. Can you group that? So if I split that, I've got 6.3 times 10 to the power 5. All right. So using your index law, you know that that will be 10 to the power 5 minus 6. 6.3 divided by 7 is 0.9, correct? Now, is that scientific notation?
No.
No. So how do you change it to scientific notation?
9.
Yep.
Negative
9 times 10 to the power minus 2. How about part C? Part C is an interesting one. You've got square, you've got square. Alright, using your index law, bring the square inside the bracket. So I've got 1.5 to the power of 2, which is 2.25, times 10 to the power of 10, times 9, times 10 to the power minus 12. So therefore I've got 2.25 times 9.0 times 10 to the power of 10 minus 12. So therefore 9 is 20.25, I think, times, yep, times 10 to the power of minus 2. Is that scientific notation?
No.
No. How do you change it?
3.02.
Thank you. 2.025 times 10 to the power of? Thank you. Good. So now you can see that you can use your index law to actually simplify some expressions. The next bit, significant figure. This is interesting. All right. Let's say I tell you the length of a rope is 20.5 meters. is that exact? Can you measure it that exactly? Probably not. Your eyes and my eyes are slightly different when we read something like a ruler or a tape measure. So something like 20.5, I would say that the range is between 20.45 meters and 20.55 meters. All right? Significant figures is important when you do calculation. Alexi, focus please. In terms of, I would say some engineering calculation is important. Whereas I know for me, when I was doing designing of buildings and stuff like that, I don't really care because I work in a factor of safety of about 5 or 6. So if I put in a factor of safety of 5 or 6, sometimes the significant figures doesn't matter. However, there are a lot of situations you do need to think about significant figures. So if I say Doris's height is 158 centimeter, it will probably be between 157.5 and 158.5 centimeter. It's pretty hard to get the exact. Right? So calculating numbers, significant figures could be important, it could not be. All right. For example, like I say, when I was looking at designing a building, what we do is, if we design something and it's, say, 2 meters, if we could whack in a safety factor of 5, I don't really care about the significant figures. Whereas, you do need to think about the actual length, sometimes in significant figures. All right, so this actually highlights the level of inaccuracy and uncertainties, and we have to deal with uncertainties all the time. Now, let's have a look at all these things here. All these numbers, I derive it from 6025. First one, I say that it's 4 significant figures. Second one, also 4 significant figures. Let's concentrate on the first two. All right. Why do I say the first and the second, both of them have 4 significant figures? 4 numbers. Right. But you've got more than 4 in the first one. Yes. All right. When you say the 0 don't count, what about the 0 in between? Why did I count that?
The spacing 0 counts.
Yep. So 0 before the first number is not to be counted. Those are called the leading zeros. Second one, 0 in between 2 numbers is to be counted, called the trapped zeros. What about this one? Why did I say 5? Why did I count everything?
Because 0 is after.
0 after, because it's telling me that there could be more. So it's significant, 5 significant figures. This is called the trailing zeros. That could be numbers still behind it. All right? So we don't know what actually is there. It could be you're giving this to 3 decimal places, but you've got 5 significant figures. You don't know what is behind that. Why do I say this one is 4 significant figures? The 0 after the 0 at the end are not counted. So it's very different when you've got decimal place and no decimal places. If you've got decimal, the 0 at the end must count because you know there are numbers behind it. In this case, it's probably an integer. You don't actually have to count what is behind it. So that's probably it is an integer. You know that there's no decimal, that's nothing. Whereas this one, you've got a decimal. A decimal is shown, so you could assume that there will be numbers behind it. So therefore, that is 5 significant figures. All right? Zeros at the end must be counted because of the decimal. And finally, what about this? We actually ignore the power of 10. So there's 6.025 times 10 to the power of 4, which means there are 1 extra 0 is actually 60250. and the 0 at the end, we don't count. So the power of 10 is scientific notation, is not significant. All right, so think about the significant figures. The 0, in between, two numbers you have to count. At the end, if there's a decimal, you must count. If not, you don't count. Before, you don't count. If there's a decimal, after the 0, you count. And anything to do with scientific notation, you don't count. All right. So, how many significant figures for the first one? Next one? Then? 1 and 3. All right? The two zeros don't count, so that's 8. The 0 counts because it's 8.0. There's no decimal, so I don't count that. That's just 800. That one I do count, although that one I do count because of decimal. All right? Now, exercise 2, 3, and 4, please. That will probably take you about 5 minutes. I will leave this on the board so that you know.
Okay, so at this stage, when you want to say that GX, you don't worry about that. Okay, so you need to convert it to decimal without rounding to specific number. Oh, okay. Without rounding to specific number. Yeah, that's fine.
Like 10 different terms.
Yeah, of course. For fraction, you can't say anything. Yeah, fraction, you can't say anything significant figures.
Hey guys, my bad.
So you've got 6.61333. Without rounding. So, when the question said without rounding, if you've got something like 3.23333, that will be 3.23 with a dot on top, without rounding. Or you've got, say, 2.6454545, without rounding is 2.645 with a bar on top. It just indicates that it's repeated all the time. That's all. Stop at exercise 4, all right? I will upload the solution a little bit later. All right, can I move on to the next part of the lesson, or you still need a few more minutes? All done? Not quite yet.
Yeah.
Yes? Six. Oh no, don't worry about that. You don't have to say anything because it's a fraction that I've given you. So
Don't do anything with that.
you don't have to say anything. 66.6%. All right. The bar is usually used when you've got 2 or 3 figures that's repeated. Dot is just one single that is repeated. All right, when you're ready, let's concentrate on the whiteboard, please. All right. Last bit of the lesson, and then you've got some exercises you could do. Now, let's think about operations with significant figures, adding and subtracting. All right. So when adding and subtracting with significant figures, the final value must only have as many decimals. Adding and subtracting, you've got to think about decimals as the original value with the least number of decimal places. Alright? So that's how you should round it for adding and subtracting when you're dealing with significant figures and decimal places. For example, the sum of 4.435 plus 1.9348, the least number of decimal places is 3. So the answer when you're given, you must give it to 3 decimal places only. That's important in terms of accuracy, especially when you're thinking about how accurate can you go up to 4 decimal places, or how accurate you can go up to 3 decimal places. So if you've got 3 decimal places is one of them, the other one is 4, you round it to 3 decimal places only. That's adding and subtracting. Yep.
Why is it the least number of decimal places and not the least number of sig figs?
Because it could be 4 plus 2.345 or 4.0 plus 2.345. So you may have to have one extra one.
So this part of like, would this be part of the exam?
Probably. All right. Next one, multiplying. Multiplying and dividing is least significant figures. All right? So that's the difference between adding and subtracting, multiplying, dividing. You have the least significant figures. So for example, the product of 2.05 times 132 times 1.7. The least number of significant figure is 2. So the answer must be given to 2 significant figures. We're not worried so much about the decimal place now. Multiplying, dividing, it has to be significant figures, 2 significant figures, based on what your original number is. So that's just the difference between adding and subtracting and multiplying and dividing. That's all. Adding and subtracting, least number of decimal places. Multiplying and dividing is least significant figures. All right? Now, although in the exam most of the question you'll be asked to give your answer to 2 decimal places rather than significant figures, unless the question specifically asks you to give certain significant figures. You got to be very careful, all right, in terms of exam. That should be the end of the lesson. You got exercise 5, and then you can start thinking about your what I've taught you today. Exercise 5 plus, of course, the usual exercises on Google Classroom. And I've uploaded a couple of chapters from Club and I think 1 chapter from Nelson. Please download that and keep that.